Hi, and welcome to this week's online discussion. So for this problem, we want to consider a planet that is orbiting a star at the origin. And the position of the planet is given by RT equals R1 cosine omega t, R2 sine omega t, and 0, where R1, R2, and omega are positive numbers. So this orbit is going to be, just from the form of R, an ellipse on the plane z equals 0. We want to find the velocity of the planet at each time t and compute the rate of change of the angular momentum, which is given by r cross v. So if we have a particle with position given by rt, then the velocity via t is just equal to the tangent vector at each point of the particle. So it's going to be r prime of t. And r prime of t is just given by derivative of each coordinate. So it's going to be r1 cosine omega, the derivative of r1 cosine omega t, which is omega r1 times negative sine omega t. Second coordinate will be the derivative of r2 sine omega t, which is going to be omega r2 cosine omega t. And the third coordinate will be just 0. So this is the velocity. So now we can compute the angular momentum, which is going to be equal to r cross v. This is just r cross r prime. Well, of course, at this step, since we already know both r and r prime, we can compute the cross product in the regular way, and then take the time derivative, which is d dt. But that will be a very long way with a lot of computation. So another way is just to directly compute using the product rule for cross products, dtt, the time derivative of the angular momentum. So the rate of change of the angular momentum is just ddt of r cross r prime. And by the product rule, this is just r prime cross r prime plus r cross r double prime. And notice that r prime cross r prime is going to be 0, because any vector cross with itself is going to be 0. So this is just equal to r cross r double prime. So now we can just compute what is r double prime. So r double prime of t, the first coordinate, we just differentiate this thing again, and then we will get omega squared r1. Sorry, we have the negative omega squared r1 cosine omega t. And the second coordinate will be negative omega squared r2 sine omega t. And we have 0. And we see this is equal to omega squared times negative r1 cosine omega t negative r2 sine omega t and 0. Comparing this to our original r here, so we see this is exactly negative omega squared rt. And therefore, my rate of change of angular momentum, which is going to be d dt of r cross v, this is d dt of r cross r prime, which we computed is r cross r double prime, but r double prime is negative omega squared rt, so this is r cross negative omega squared rt, and we can pull the negative omega squared out, so this is negative omega squared times r cross r. But again, r cross r is 0. And so this is 0. So the rate of change of my angular momentum is 0. And what does this tell us? This says precisely that angular momentum is conserved. Since the derivative is 0, the angular momentum at each time would be constant. And therefore, it's conserved.